Hi friends, a very good evening and thank you for joining in today. Could you please confirm in the chat window if I'm clearly visible and audible? Could you please confirm that, please? Again, you can refresh the window once to see the chat. I think it just got enabled as soon as I started the streaming. So is everything clear? Yeah, I can see everything at my end fairly clearly. Okay, good. So since we are a few minutes early, again, I have the whole chat window on my phone also. So we will start the session in about 3-4 minutes, right? So we'll just wait for everyone to join in because many of us are slightly early today. Cool. So no glitches, good. The audio is clear. Okay, good. Hey, I'm just curious. How many of you have used OpenCV till now? Just curious. Those of you who have can just respond in the chat window. How many of you have ever tried playing with OpenCV in C++ or Python? Either of the languages is all right. Okay, that's my last minute alarm. Just to make sure that I'm not late. Okay, some of you have used it. Okay. Okay. Yeah, I mean, if you know Python programming, it's fairly easy to pick up, but good. Some of you have used it for image processing, etc. Cool. So we will start with the basics. Again, most of OpenCV as a library is very simple to use if you know Python programming. Of course, the internals of how these algorithms work is like 4 semesters worth of coursework, right? Because today in OpenCV, there is everything from classical image processing or digital signal processing to state-of-the-art in deep learning, right? You have YOLO-like algorithms also, which are possible, object detection algorithms in OpenCV. So it's a very, very large library. I have been using it for at least since 2007, I think, yeah. My BTech final year project was using OpenCV. So I've been using OpenCV since 2007 onwards. So yeah, cool. Yes, so this session is going to be very introductory. All the only assumption or the prerequisite that we are expecting is Python programming. We will not assume any knowledge of image processing or computer vision. We'll start with some very simple examples. I will cover the underlying mathematics to the best of as best as we can within the limited time that we have. I will not be we'll also use some slightly complex algorithms. There is one algorithm which uses Gaussian mixture models. I'll not be able to explain all the underlying math, but I'll give you an intuition behind it. For other things, we'll use simple matrix operations, which are simple and easy to understand, right? So that's where we are. Cool. Some of you plan to use it for your final year project. Actually, my final year project in BTech in 2007 was using OpenCV to do some interesting stuff. So my BTech project last time was, in my BTech final year was, I would take these laser pointers that used to be very famous in those days, in the early 2000s. So my webcam would see what I'm drawing on my laser pointer on the wall. And if I draw an arrow which is pointing forward like this, all this is being drawn using my laser pointer, then it would skip to the next song. Or if I drew an arrow which is downwards, then it would reduce the volume. So it was basically sort of simple gesture recognition using these laser beams with a small webcam. It was like a 100-line code, and I wrote it in C++ those days because I was not very comfortable. I don't think Python existed. OpenCV's Python wrappers did not exist then, if I'm not wrong. So yeah, so that was my BTech project. So Neeraj, SLAM is a semester-long course, right? So we will not be able to cover SLAM. Again, this is not an OpenCV course. This is not even a computer vision course. The SLAM is something that is something that I've personally worked on, because in the previous startup that I co-founded with another friend of mine from Indian Institute of Science, we built these 3D reconstruction algorithms using smartphone cameras, using a lot of multi-view geometry. So the whole SLAM multi-view geometry is a big area. That's like almost 2 semesters worth of coursework, right? So I don't think we'll have time to go too deep into it. Again, this is an introduction to get started with OpenCV. Hey, it's 7:01, so let's get started anyway, since most people, since we are already a minute past 7. So just before we go there, quick note. So we will try and spend 90 minutes back and forth. Again, I'll focus on simple methods. We'll take up some simple image processing, computer vision problems. I will solve them for the next 90 minutes. And in between, if time permits, we can go back and forth. I'll see some of your answers and things like that. But at the end of 90 minutes, we'll have dedicated 30 minutes for a Q&A. I thought this is a better model so that we can cover the 3 or 4 problems that I want to solve today using basic OpenCV and image processing algorithms. So 90 minutes, let's try to solve 3 or 4 problems. And 30 minutes, we'll do a Q&A. I hope this is clear. So I'll not be looking at the chat window actively while I'm teaching. If I'm asking a question, I anyway have the chat window on my phone. I'll keep looking at it, right? So I'm just sharing my screen. Just let me know if everything is visible and audible, even after I share my screen. Again, I will simply be using a Google Colab. So can everybody see my Google Colab notebook? Can you please confirm that in the chat window? Can you see my Google Colab notebook? I can zoom it in a little, if that helps. I will share this whole Google Colab notes. Can you guys please confirm if you can see my Google Colab notes? Yeah, it's clear, right? So somebody is asking for good resources to learn OpenCV. I will surely point to that. Ritik is asking, do you know GeoHot? Yeah. Phenomenal guy, obviously. I've seen some of his code also. I follow his, so GeoHot is this phenomenal hacker / computer engineer, phenomenal guy. I see some of his lengthy videos, like 4-hour, 6-hour live sessions that he does. I really enjoy his work because he's a great geek engineer, like core great engineer. So cool. So again, I'll be sharing this Google Colab notes with all of you at the end of the session. So just please follow with me. Okay, so let's get started. So this is basically an introduction to OpenCV. For those of you who don't know much of OpenCV, this is a very good introduction to get started. Again, in our course itself, we have covered OpenCV at various points, primarily in the context of computer vision problems and image processing problems and case studies, right? So we have a case study where we build a self-driving car, the brains behind it, where we have covered and used OpenCV extensively. So here we'll not take up such complex problems. We'll start with much simpler problems. So the objective here is to solve some simple image processing and computer vision problems using OpenCV. So I have about 3-4 problems. We'll try to solve them. We'll start with the problem. We will understand how to solve the problem from a mathematics standpoint and also solve it using OpenCV. I'm not assuming a lot of mathematical knowledge. All that I'm simply assuming is you have basic knowledge of 11th, 12th class matrix algebra. Again, if you have forgotten it, don't worry, right? So again, we'll try to understand how to use OpenCV for other tasks beyond the 3-4 tasks, simple tasks that we will solve. Okay, it's a very simple library. Once you get used to it, it's very simple to use. Also, we will cover simple to understand examples. We will not be able to cover advanced examples because we are not making any assumptions about your prerequisite knowledge of in-depth matrix algebra or signal processing and things like that, right? So the only prerequisite we are assuming here is a working knowledge of Python. Again, you don't have to be an expert in Python. If you have decent working knowledge, if you can write basic code in Python, if you know what is a class, what is a function, basic stuff, I think you're good. Most important skill is, can you read the documentation, official documentation of various libraries, and can you Google search? If you can do this and if you have basic knowledge of Python, you will be able to follow through this. Okay, so as somebody was asking, modern computer vision today is a fairly big field. It's a massive field, right? It's fairly large today. So if you take modern computer vision, again, if you want to become an expert in modern computer vision, there are many, like computer vision is this big area which has borrowed concepts from many areas. Like for example, if you're an electronics student, you might know about digital signal processing. There is an analog signal processing that communication engineers use extensively, but there is a digital signal processing also. So a lot of computer vision algorithms and image processing algorithms use concepts from digital signal processing like Fourier transforms, etc. Similarly, there is the classical image processing methods using convolutions and things like that. Then a lot of modern computer vision uses machine learning algorithms. I'll show you one example in the problems that we solve, right? So there is a lot of machine learning algorithms that are used extensively in modern computer vision. Like here, machine learning algorithms are used, right? Again, modern computer vision also uses a lot of linear and matrix algebra. More specifically matrix algebra than vector algebra. So it uses a lot of matrix algebra that you may have learned in your 11th and 12th class. Then there is, like, most of modern computer vision also uses a ton of deep learning. And the reason behind it is very simple, because right now we have this SOTA. SOTA basically means state of the art, right? Most of the state of the art algorithms in computer vision are often solved using deep learning algorithms, whether it is recognizing objects, whether it is segmenting something from the background. A lot of these things are deep learning driven. So more and more of computer vision is becoming deep learning based, and it's just a natural progression. Then there is this whole area called computational photography, which is a graduate level course onto itself, which is like this has become very, very popular because of the explosion of smartphones. Okay, I'll show you some pointers to how to use computational photography using OpenCV. For example, okay, let me just show you that, right? Let me just show you computational photography, what it can really do. So again, I'll provide all the links to this. So this is a great set of tutorials in Python for, okay, this is only image processing. So if you just go here, these are OpenCV Python tutorials. I will provide a link to this here. So okay, reconnect. Okay, so you have OpenCV tutorials here. This is the link that I'm pointing you to. So this has a lot of very nice, simple to follow tutorials, and I'll borrow a lot of code in this discussion also from these tutorials so that you can go back and learn. So these are all the sub parts of OpenCV today. So there is this whole thing called computational photography, like which is let's say high dynamic range, right? So what does a high dynamic range mean? So again, very nice explanation of it using these diagrams. Using our smartphone cameras, we can take, suppose you have a night scene, right? You can take photographs. This is an overexposed photograph. This is an underexposed photograph. This is also slightly overexposed because there are too many whites here, there are too many blacks here. So what a lot of smartphone cameras do as part of high dynamic range photography, which is there in most advanced smartphones today, is it takes multiple pictures with multiple exposure times. Here, the camera is exposed for a long time, or in other words, like for example, there is some data given here. Basically, this photograph is taken at night by opening the camera shutter for a long duration of time so that more light comes in. Here, the camera shutter is open for a smaller amount of time, so there is less light that is coming in. Now, all these 4 photographs can now be combined very smartly to arrive at a photograph like this. Just look at this photograph. This is using one of the algorithms for HDR, right? A lot of your high-end flagship products, actually flagship smartphones do this, right? So again, this is not such a good output, but this output is pretty good. Again, these are different algorithms that are used for arriving at the answer, right? So here, computational photography is something that has become, sorry, my bad. Okay, so computational photography is something that has become very popular in the last 5 to 10 years. There are even graduate level courses in computational photography taught at universities like Stanford. I mean, phenomenal work, even a lot of research done at companies like Google, Facebook, etc. Then there is this whole area called multi-view geometry. This is something that I have worked on extensively in my previous startup. And multi-view geometry is all about, okay, let me just show you that. Let me just show you a simple image on what multi-view geometry can do. Okay, let me just show you this. Okay, so multi-view geometry is, okay, let me see if I can get a clean, nice picture here. Okay, I can show you this, but this is the textbook. Again, this is the seminal book called Multi-View Geometry in Computer Vision, which is like a 2-semester worth of coursework. So what it does is, okay, so let me just draw it and show it to you. So what we do in multi-view geometry is this. So suppose you have a 3D face, right? Suppose you have someone's face here. You take a picture of this person, some 3D object. You take one picture from, let's say, this with your camera this way, placed this way. You take one more picture with your camera placed this way. You take one more picture with your camera placed this way. You take one more picture with a camera close to the subject. You take these multiple pictures using a camera. Now, using all these, remember a picture is a 2D thing, right? Using all these pictures, can you combine all these pictures, right? And create a 3D object. That is the task behind multi-view. That is one of the most important applications of multi-view geometry, right? So you are trying to construct the geometry of this object using multiple views which are captured through cameras. Right? This is again one of the most important tasks of multi-view geometry. Again, there are like structured motion. Again, multi-view geometry is also used in robotics. There is a whole class of methods for something called a SLAM, which is localization based algorithms. So we will not, again, this is a big area. Somebody who wants to become an expert in computer vision, typically, again, each of this, like multi-view geometry is 2 semesters worth of course. Computational photography is typically at least 1 semester worth of course. Deep learning is at least 1 semester. Machine learning is 1 or 2 semesters worth of coursework. Image processing is typically 1. DSP is typically 1 semester worth of coursework. So a typical computer vision has all these sub areas. So becoming expert at it typically takes years of effort. But if you're interested, there are a bunch of very nice resources that you can get started. Again, OpenCV is probably the most influential library in computer vision. So OpenCV stands for, the CV stands for computer vision, Open stands for the open source. I have been using it for at least 15 years now. I'm sure it was even there prior to this. Again, it has become very good over the years. So if you want these tutorials, there is a link here. If somebody wants to read a book, there is this very nice book. So let me just open this. There is this very nice book by Richard, I don't know how to pronounce his second name, I just call it Richard S. So very nice book. I think he's currently at Facebook, okay, or he used to be at Microsoft Research. Very nice book. There is a preprint, there is a first edition that is available publicly. There is also a draft copy of his second edition that is publicly available. You can read it. Again, this is a very nice book because it covers a lot of these things in a single book. So if you are somebody who likes reading a book, the Computer Vision Algorithms and Applications by Richard Slizewski is a very nice book for sure. So if you want a good blog, there is this PyImage Search, which is a very nice blog with specific focus on Python, also on computer vision specifically using OpenCV, right? A very nice list of very nice blogs. Of course, they also use TensorFlow, Keras at some places. But they use OpenCV extensively. Very nice bunch of blogs, very informative, very simple to follow. So if you want additional resources beyond this session, here are some great resources. But don't get overwhelmed by all that is there here to learn. It's perfectly okay if you start slow, if you want to become an expert in computer vision. The most important thing that you have to learn is surely deep learning, which is the most important thing in computer vision today. The other areas you can slowly learn and build your skills step by step. So within computer vision, most computer vision engineering roles today expect you to be an expert in deep learning and machine learning, because a lot of classical image processing and digital signal processing approaches have been replaced by deep learning and machine learning approaches, right? So that's what I would recommend. So let's go into some problems, right? Let's start with something simple. Okay, so the first problem that we will tackle, let me look at the chat window if there are any issues. Okay. Cool. Okay. I'll share the Google this collab notebook at the end of the discussion. Okay, I'll surely share this. It will be publicly available. You can copy it, play around with it, and change it. Okay, cool. Let's get started. So our first problem is called image blending problem. Again, this tutorial that I have here is heavily based on OpenCV's official tutorials that you can read from here. So I've taken a lot of code from here and I've reused it, modified the code as we need it. Again, there will be some differences between the code that are there in the OpenCV official documentation and this, because here I'm running everything in Google Colab, not on my laptop. Again, the reason I'm using Google Colab is because whatever computer you have, you can still run it without any headaches of installation. Right? So, okay. So let's get started now. Okay. So a bunch of libraries that we're importing. The most important ones here, again, again, we all know NumPy, we all know Pandas. This is the OpenCV library. So import CV2 as CV. right? There was actually OpenCV version 1, version 2. Right now, I think version 4 is going on. But it was OpenCV version 2 which first had a Python layer. Again, just to give you some context, most of the functionality in OpenCV is written in C++. Because remember, a lot of image manipulation operations are very expensive computationally. So OpenCV is natively written in C++. But on top of this C++ layer, there is a Python wrapper that is there. So when you write Python code, what happens is this Python code implicitly calls C++ code which runs. Again, this is exactly the same strategy that even TensorFlow uses, right? If you take TensorFlow, which is one of the most popular libraries for deep learning, a lot of the core functionality of TensorFlow is actually built in C++, but we are given a Python layer on top of it. Because Python is easier to use for non-experts, C++ has its own challenges like garbage collection. You have to be a good software engineer to be able to use C++ well. Right? I've used OpenCV both in C++ and Python. I personally prefer Python because it's easy to get started, especially if you're a beginner. If you're an advanced user, you can certainly use C++, right? So import CV to as CV. We are just importing the whole OpenCV library here. That's what this means. Okay. Now, because we want to use some of the functionality of OpenCV in Google Colab, we have to import this special function here. This is called cv2_imshow. In actual, if you're running this code on your computer, you don't have to import this. It is only because we are running this code in Google Colab. From google.colab.patches, you have to import this simple functionality to display images. I'll show you if you're running this on your laptop, you can change it slightly. While I've imported skimage, which is again a image processing library, and PIL is to basically load images, write images, etc. I have not used them extensively here. Okay, this is your standard matplotlib. I have not used matplotlib also extensively. Okay, so let's first understand. So this is just importing all the libraries. Before we go there, what is image blending problem? Let me show you the output first. So this is a photograph of the famous footballer Messi, right? So some very famous shot of his. Now imagine on this photograph, if I want to blend another photograph on top of this, or blend one more photograph with this, right? Suppose, imagine if I have, this is OpenCV logo, by the way. This is the logo of OpenCV. Suppose if I want to blend this OpenCV logo and Messi's picture. Okay, where is this? Where is the output? Okay, so look at this output. This is what is called as image blending. Now we have generated a new image here, combining the Messi's image along with you've blended the OpenCV logo with it, right? So how do you achieve this? It's not rocket science. It's a very simple process, literally 5 lines of code. But let's understand the mathematics behind it and also how to use OpenCV, the foundations of OpenCV, while solving this problem, right? So this is the output that we are expecting to achieve. Cool. So let's go step by step. I'll also point you to some errors that typically you come across with OpenCV so that you learn how to fix them. So first, what I'm doing here is I'm downloading the image, right? So if you want this, so this image is called messi5.jpg. It is there on GitHub. First, I have to download it to the computer, right? As all of you might know, people who use Colab, what happens, the way Colab works is as follows, right? So Google has all these servers, right, on its cloud. In one of the servers, your Google Colab is actually running through some virtualization and other operating systems concepts. So this Google Colab is running on one of the Google servers, right? So this is, and you're able to see this Google Colab through your web browser. So it is not using the computational resources of your browser or your personal computer. It's using the computational resources of the server. So when you want to use any file within this, you first have to download. Suppose if you want to download an image and use it in your Google Colab, you have to download that to the server, right, to which you are assigned to. So first what we'll do is we'll first get that. So there is this in Google Colab, if you want to execute any command line, again remember the Google server is a Linux server. It's a Linux or a Unix server in the backend. So all commands that you can run in a Unix terminal, you can run on this server here. So what this does now is, because I've put an exclamation here, this says that this is not a Python command. This is actually a Linux terminal command. wget basically means get from the web, right? Wget here stands for web get. So what I'm saying here is get from the web. This is the URL, get it from this URL, get this file from the URL, and -o, which means save it with an output messy5.jpg. Very simple. This is literally saying, this exclamation is saying, please run it on the Linux terminal on the server. Run this command wget, which is webget, get from a website. This is the URL. Store it on your local computer as messy5.jpg. The moment you execute it, it will take a few seconds. It will download everything. Now, if you want to see whether this is downloaded or not, all you have to do is you say ls-l. Again, this is a very simple Linux command for those of you who may not know. Exclamation basically means it is going to run on the Linux terminal. Linux terminal is nothing but the Linux command line prompt, right? So you have your Windows command line prompt, right? So just like your Windows having command line prompt, Linux has something called as terminal. So it will run this command on the Linux terminal now, right? So all that we are asking it to do is we are saying, okay, list, this is -l basically means long form. So list all the files which are there in the current folder. In the current folder, these are the files that are there. Messy5.jpg is there, which means it is successfully downloaded. I'm just checking whether it's downloaded or not. Now I want to see the downloaded image first. Very simple. Remember, we have imported OpenCV as CV, right? So first let's see this image. If you want to display an image, it's very simple. You say cv.imread. Im basically means image read. This is the function, right? CV basically means your OpenCV. Within OpenCV, there is this function called imread. Im means image read. You give the path to the file that you want to read. Since you're in the same folder, you just say messy5.jpg. Very simple. Then this will create a variable called img1. Again, this result I'm storing it in img1. So now img1 contains this messy5 image. Now, if I want to show this image, right, in Google Colab, we will use this function called cv2_imshow. Remember, we have imported this from here. If you see this line of code here, cv2_imshow is a functionality that we have imported from Google Colab patches. If you are running this on your personal laptop, not on Google Colab, then this function will change slightly. This function should be not cv2.imshow, it should be cv.imshow. That's it. It's a small change. So if you're running this, if you download this IPython notebook and run it on your computer, if you have OpenCV installed, installing it is fairly straightforward. It's just a pip install, right? Those of you who know Python already know how to install using pip, right? So you just say, because we've imported OpenCV as CV, you just say cv.imshow and show img1, it will show the image. It's as simple as that, right? Okay. So the image that we wanted to get, now we have verified that, again, remember the steps. We have downloaded the first image. We have ensured that the first image is there in the local path. We have also seen the image to verify that everything is all right. Now let's get some properties of this image. Okay. So if you print img1.shape, right? So img1 is the image that we have. It has a property called as shape. So if you print this, you get a tuple like this. What this is saying, very interestingly, what this is saying here is that the image has 342 pixels by 548 pixels by 3. That is the size of the image. Let me explain how the size of the image is measured. Okay, this is very important and interesting on how images are internally stored. So what it's saying here is this height of the image here. This height of the image here is, what is the number that it says? 342, right? So it says this image has 342 pixels height. It has some 500, what is the number again? I forget the number. 548 pixels wide, right? So it has 548 pixels wide. So these are the dimensions. The first one is the height of the image. This is the width of the image, and it says 342 cross 548 cross 3. This 3 corresponds to the fact that there are 3 colors here. This image is represented using red, green, and blue. Let me just show you this. Let me just zoom into an image and show you how it works so that you can better appreciate it. Just give me a second, folks. I have this messy image downloaded. Okay, so I've just downloaded this image now. Look at this. If I keep zooming into this image, okay, if I keep zooming into this image, again, I've just opened this image in an image viewer on my computer. right? So I'm just zooming in. If you keep zooming in, okay, it's not letting me zoom in beyond this, but look at this. Each of this is basically a pixel. So your image is basically a bunch of pixels. For each pixel, you have three values corresponding to it: a red, a green, and a blue value. Typically, in most representations, these values lie between 0 to 255. 0 means the smallest value, 255 is the largest value. Right? Very simple. Imagine if R equals to 0, G equals to 0, and B equals to 0. That means what you have here is a black pixel. Right? If all three of them are 255, 255, 255, then what you have here is a white color. On the other hand, if the red pixel is 0, if the green, for this pixel, for every pixel, there are three values here. Right? If the red component's value is 0, the green component is 255, and the blue component is 0, then the pixel that you have here will be a green pixel. Then what you have here is a green pixel. So every color can be generated, or at least a vast majority of colors can be generated using a combination of red, green, and blue. This is how computers actually store images, right? So what we have seen here in this code is basically saying that this messy image that we have here has 342 pixels height. Okay, 1 second. Okay, so it has a height of 342 pixels. It has a width of 548 pixels. And for each pixel here, there are three values corresponding to red, green, and blue. That's what it means, right? So you can also think of this, if you want to think about it, you can also think of an image as three matrices. Look at this. You can also think of an image as three matrices if you want to think about it mathematically. The first matrix corresponds to all the values of, see, for each pixel, there is a red value, there is a red component, there is a green see, for every pixel, there is a red component, there is a green component, and there is a blue component, right? So you can think of it as three matrices, one matrix corresponding to all the red components for each pixel, the G, so the B, right? So you can think of it as three matrices with a height and width, same height and same width, same height, same width, same height, same width. So you can think of an image as basically three matrices of the same height and width, where the first matrix corresponds to each pixel. Again, this is a matrix, right? Matrix has rows and columns, right? Matrix has rows and columns. Each of these cells correspond to a pixel now. So this left top pixel, whatever is the red value will be the red value here. Whatever is its green value will be the green value here. Whatever is its blue component's value will be the blue component here. So mathematically speaking, an image is basically a stack of three matrices, right? If this is a color image, by the way, we are talking about color images only. That's why there are three here. So again, if you're talking about pure mathematics, so this is your, so you can think of this as an array, right? Or you can think of it like a vector. An array can be thought of as a vector, right? Then you have a matrix here. So an array is a one-dimensional object. A matrix is basically you have rows and columns. You can think of it as a two-dimensional object. Then if you have a three-dimensional object, for example, an image, a color image is thought of as three matrices stacked upon one another, right? You can think of it like a three-dimensional array. In programming, right, you can think about it as a multi-dimensional array. In NumPy, we have these multi-dimensional arrays, right? You can think of it as a multi-dimensional array. Mathematicians also call it as tensors, right? The name TensorFlow for the very popular deep learning library comes because it operates on tensors, right? So you can think of it as a tensor, or you can think of it as three matrices because there are only three matrices corresponding to RGB here. Cool. So this is very simple. So we got the shape of it. Now I can also get the value at an exact pixel. I can say the 100th row and 100th column. What is the value of the pixel there, right? I can easily obtain that value and I can even change that value. So I can just say print img1 100, 100. So the 100th, see, look at this. The first one corresponds to the height. This corresponds to the width, right? This 100 basically says for the 100th in the height, the 100th pixel, in the width, the 100th pixel. What are its values? So it has a R component which is equals to 157, the G component which is 166, the B which is 200. So the same RGB is present here, right? So you can actually access the value at any one pixel using just this simple operation. It's actually very simple. It's like accessing any NumPy arrays with slight syntactical changes. Now, let's say I want to do something. Look at this. In this picture, I have one football here, right? This yellow colored football. If I want to do something like this, imagine if I want to cut this, area, if I want to cut some area around it, and if I want to paste it here, can I do that? Right? Then there will be two footballs, right? I want to copy whatever information is here and paste it here, so that I have two footballs here. Can I do that? Actually, it's very simple to do it. The result looks somewhat like this. Look at this. This is how the result looks like. So what has been done here, whatever is there in this region, it is copied and pasted here. Again, when you paste it here, it doesn't fit perfectly. The reason being, look at this. You can see this shape. You can see this shape that it is pasted here, because this background is not perfectly matching. But can you do that? Can you take some rectangular area here and paste it here? Can you do that? It's actually very, very simple, right? It's literally 2 lines of code. So first of all, you have to determine where is the ball. Look at this. You have to first determine in both the height axis. Look at this. You have the height axis and the width axis. So on the height axis and the width axis, first you have to determine where the ball is, right? So the ball here is, so I just create this object called ball, where I say image 1 280 to 340. So I'm saying rows 280 to 340. Again, what is my largest row is 342, right? So I'm saying 280 to 340, which means row number, because the height, this is heights, right? 340 to 480 will be somewhere in this region. Sorry, not 340 to 480. What is the number that I used here? 280 to 340, which means the roughly the last 60 rows. So I'm taking this rectangle here. In terms of height, it is 280 to 340. In terms of the width, right? So if you think about it in terms of rows, I'm saying row 280 to 340, column 330 to 390, right? This whole thing roughly corresponds to, again, I've verified it manually. It roughly corresponds to somewhere this area, roughly corresponds to this area. So whatever are the pixel values here, I'm copying all of those pixel values into a variable called ball. That's what I'm doing here. Very simple operations. Okay. So whatever is the information that is there in these rows and in these columns. So these rows and these columns define a rectangle in the image, right? Starting from 280th row to 340th row. In terms of columns, the first column is 330 column to 390 column, right? So it's defining this whole rectangle. Now for this rectangle, all the information that is there in this rectangle, which is the actual ball, I'm copying into this variable called ball. And now I'm saying, take the original image. In the original image, in these rows and in these columns, copy whatever information is there in ball, paste it here, right? So very simple. So what we are doing here, we are taking the information that is there in this region, right? Sorry, let me draw it properly. So we are taking the information that is there, all the pixel values that are here, and we are pasting it at a different place. That's it. So the moment you do that, and the moment you say, hey, now let's see the image, let's show the image, right? Then you just say cv2_im show img1. What happens? Now the ball is there at 2 places. Very simple manipulation of images, literally 5 lines of code. Okay, but this is not image blending, right? You have just copied some information from here and pasted it here. Now, as I just told you, how is an image represented by a computer? We have zoomed in and seen it. One idea, one very interesting idea, because we know that an image is represented as 3 matrices, right? You have R, G and B. So an image is literally represented as 3 matrices R, G, B, each of them having a specific height, the same height and width, basically same height and width, right? So the moment you have these 3 matrices, the first thing that you should think of here is, look at all the mathematics that you already learned in your school days, right? You have a bunch of matrices. You can do all these algebraic operations on the matrices, right? You can add matrices, you can subtract matrices, you can multiply matrices, right? So while this is actually, it's actually an image, but I don't care about it. The moment I convert it into a mathematical representation as 3 matrices, I can use all the mathematics that I learned in my high school to solve some interesting problems. So actually a lot of image processing is actually applied matrix algebra. Of course, there are some exceptions, there are some signal processing operations, but a lot of Lot of image processing operations are simply matrix algebra operations that you learned in your college, in your 11th and 12th class. It's just an application of it. Unfortunately, we were not taught that when we were in high school. Okay, so let's do one thing. Okay, let's actually see some addition that I'll just try and apply here. I will actually apply addition to combine both these images. It's a very simple example. Again, the key takeaway for you is, here is that you can just use simple matrix algebra operations that you learned in your high school to solve a lot of image processing problems. Okay, that's a key takeaway. Now let's download OpenCV logo. Again, very simple to download. Same wget, the webget function. I know where it is there on GitHub. I just download it and I save it. Right? Simple. Now again, I'm just loading this image. Look at this. The same functionality. I'm just loading this OpenCV logo in an other variable called img2 and I'm showing it. Same functions. We have seen how to use imread, imshow. Right? So here it is. We have both of them. Very nice. What is the shape of this image? This image has a height of 600, a width of 487 and 3 pixels and 3. This 3 corresponds to a color image with R, G and B. Right? Very simple, nothing very fancy. So we have loaded both the images. We have understood that images are represented as 3 matrices, color images. Now what is image blending? Now how do I blend these two images? There is a very simple way. So image blending basically corresponds to addition of matrices with some weighing. Okay, so there is a very nice mathematical equation explained in the OpenCV blog. So let me just open that for you and show it to you. Okay, here it is. Okay, let me just zoom in a little. Again, I'm trying to explain as much as possible from the OpenCV documentation because even after this session, I want you to get comfortable reading these tutorials and documentation because that's a skill that you can take even beyond this session and start applying it to new problems. Okay, so what is image blending? Let's see this. Suppose you have two images. So you have an image f0x. Again, this f0x basically means, again, this is just a mathematical way of writing it. But let me just show you what it means. Suppose you have a matrix like this, you have another matrix like this. Okay, let's assume this is f0, this is f1. Let's assume there are two matrices, right? So, or you can call it f0 matrix, f1 matrix, right? What if for each pixel, remember, they both have to be of same size first. Let's assume they both are of the same size. Take any pixel here, right? You multiply this pixel by 1 minus alpha. You multiply this pixel by alpha. Remember here that alpha lies between 0 and 1. Take a value like alpha. So for example, imagine if alpha is 0.7, okay, or alpha is 0.3. You can pick any number of your choice. Okay, one way you can say here is, what if this number is 0.7 and this is 0.3? That's what this means, right? If alpha is 0.3, 1 minus alpha is 0.7. So what we want to do here is, again, this alpha lies between 0 and 1. So we multiply each pixel's value, all the 3 RGB values, right? So when I draw this, I mean there are 3 matrices here. That's what I mean. There are 3 matrices here, RGB. For each of the pixel values, I'm going to multiply the pixel value with 0.7 and that will result in some matrix again. To that, I will simply add the same pixel, the corresponding pixel, same pixel here also, right? Same pixel here also, I will multiply this with 0.3. And this will generate again another image for me, right? Again, remember, this is RGB. Here also you have RGB. Here also you'll get RGB, right? This is the simple idea here, which is represented mathematically. What it's saying here is, imagine if one image is f0x, the other image is f1x. You can multiply f0x with 1 minus alpha. You can multiply f1x with alpha and sum up both of them. So what are we doing here? We are just doing an addition of two matrices with some multiplication. Alright, so this is what is called as weighted multiplication. Okay, so let me just write it for you again. Suppose if I have a matrix f0, I am multiplying it with 1 minus alpha plus alpha times f1. So this returns my new image is G. Right, simple mathematics, right? Here, what are we doing here? If this value is 0.7, if this value is 0.7 and if this value is then this value will become 0.3, right? Obviously, because your alpha lies between 0 and 1. So this is not just simple addition. This is called weighted addition, because for every pixel that is there in this image, you are giving a weight of 0.7. For every pixel in this image, you are giving a lower weight of 0.3 and you are summing it up. When you do something like this, what happens is, in the final image G, you will see F0 image more prominently and you'll see F1 less prominently because you gave more weight to each of the pixel values of image F0. Right? This is called simple weighted averaging in data science and machine learning. Very simple concept. Right? It's simply, if you think of this as three matrices, right? If you think of as three matrices, you're multiplying the matrices with some scalar values, right? This value is 0.7, this value is 0.3, and you're summing it up. Right? Very simple math, nothing very fancy or complicated here. Very simple matrix operations here. Cool. So if you do that, so image blending is simply weighted addition of matrices. So let's try to do that. Now, before we go ahead and implement it, again, we can implement this from scratch ourselves. Okay. So how do you implement this from scratch? It's actually very simple. You take each image. Suppose you have your first image, let's say F0. For this first image, take the first pixel. You write a loop. You write a loop where you go through each of these pixels, each of the rows and each of the columns. So it will be like a for loop within a for loop. For each row, for each column, you take this. You'll get one pixel. For each pixel, you'll get three values, R, G and B. You multiply all these three values with 0.7, right? 0.7, and you multiply and you add to that 0.3 into the other one. This is image F0, this is image F1. So you can actually implement this using two for loops and then summing it up. You can write it from scratch. But your code will not be very optimal because you're writing these for loops in Python. Just like NumPy, it is always better to use inbuilt functionality because it is optimally implemented in C++. So there is this function called add weighted. Okay, let me show you the documentation for it. Okay, so if you just, it's very simple. You just Google search for it, you'll get the documentation. Okay, so where is it? Where is the documentation? I'm just looking for the, okay, so here is the documentation, right? Again, this is also explained. This explanation belongs to the book Computer Vision Algorithms and Applications by Richard Selinsky. Okay, I mean, it's a very tough to pronounce second name, right? So here is again, this is explained in this book, the mathematics behind it. Again, you can write, oh, by the way, I forgot to mention, you can also write OpenCV code in Java. I forgot to mention that because I have not done much of Java programming for OpenCV. I've mostly used C++ and Python, right? So here is all the explanation that you have. Where is the, okay, here is the function, right? Add weighted. So if you see the documentation for it, a lot of documentation for OpenCV is actually written, the core documentation is actually written in C++. So don't get too much confused about it. Like for example, the moment you see this, you might say, hey, what is this? This is basically C++ notation, okay, of a class and an object and class and functions inbuilt into it and things like that. So don't worry about it. There is a little bit of Python explanation also given here, okay. But actually, since everything, whatever you write in Python eventually gets executed using C++ code, here is the documentation. Here it says, the first one is basically your first source image, then alpha, your second source image, then your beta. If you want to have a gamma, you can also add a gamma. So this is how mathematically it will work. It will say your destination is your source 1 multiplied by alpha. Look at this, your source 1 multiplied by alpha, your source 2 multiplied by beta, plus if you give a gamma, it will also add gamma to it and it will return the whole output to you. Right, look at this. Again, mathematically it shows very clearly. Your destination image or your output image is source 1 into alpha plus source 2 into beta plus gamma. If you give it this way, right? So again, now let's see, this function already exists. It's very important to be able to read what the function does. Okay, so let me just show you what we have done here. Okay, we have said cv2.addWeighted image 1. For image 1, we want to give a weight of 0.7. For image 2, we want to give a weight of 0.3. This last parameter 0 basically means I don't want to use any gamma. Where is, okay, I don't want to use any gamma here. My gamma is 0, right? So the moment you do this, see what is it doing? All I am doing here is I'm multiplying image 1 with 0.7 plus image 2 with 0.3 plus 0. The moment I execute this, it throws an error. Again, being able to debug these errors is very important, especially as a beginner. The moment you see this error, thankfully OpenCV errors have improved significantly. Look at what the error says. It says the sizes of input arguments do not match. Remember that your image 1 is of a different size, image 2 is of a different size. One of the things that we have fundamentally assumed when you're doing this weighted addition of images is that the number of pixels in this image in terms of rows and columns is exactly the same as this. But our image 1 and image 2 are of different sizes, right? If you just go up, image 2 is 600 by 487. Your image 1 is, where is our image 1? Our image 1 is 342 cross 458 in terms of number of rows and columns. They don't match up. And that's why it's throwing an error. So how do you fix it? Very simple. You resize an image. Again, it's a very important skill to read these errors carefully. And the error is very clearly written that the image sizes don't match. So what do we do now? Very simple. Let's resize our image 2. Our logo image, right, which is image 2. Let's resize it. The resize function is already there. Again, if you just Google search for OpenCV resize documentation, you will get it again. Okay, so documentation, you will get it again. Okay, here it is. Okay, resize, right? Again, there are literally thousands of functions here. Okay, so here is the resize. Again, this is the C++ documentation. This is the Python documentation, right? You can just say, this is my source image and I want to represent a size of the output image. There are also nice examples given. Thankfully, a lot of this has a lot of very nice examples, right? With clear definition of what each parameter basically means. So let me show you how we use it. It's very simple. So we have our image 2, right? So we take our image 2 and we are saying, change this image 2 to have 548 columns and 342 rows. So the way you have to represent this, so if you write 342 comma 548, it's a different representation. Okay, so again, remember what is our image 1 size? 342. So let's go back and again be very careful when we write this. So your image 1 is 342 rows, 548 columns, right? But when you write the image resize, you have to be careful to write the number of columns first and then the number of rows. So if you swap them, again, the sizes will change, right? So again, this is there in the documentation. You have to just be careful when you read the documentation. Once you do that, all I'm doing here is I'm saying OpenCV resize. Very simple. I'm resizing it to have 342 rows and 548 columns. Now, to be really sure, I again print the shape. The shape shows 342, 548, 3. Right? So 342 rows, 548 columns, three colors for each pixel. I'm also showing the image. Of course, this image looks little stretched, but that's okay. We need the same sized images to make this whole thing work. Right? So cool. Now, once we have done that, I'll simply say, very simple. The add weighted function which failed earlier, right? It failed because the images are not of the same size. Now that problem doesn't exist anymore. That problem is solved. Right? So look at this. We have image 1, 0.7, image 2a. Again, I'm storing this result in image 2a. Right? I'm storing this result in image 2a. Right? So image 1, 0.7, image 2a, 0.3. My gamma is 0. I have my destination image. If I want to show the destination image, here is the destination image. If you observe carefully, the messy image, which is our image 1, which is given a weight of 0.7, our OpenCV image, which is our image 2a, because we resized it and stored it as image 2a, has a weight of 0.3. Because our logo has a smaller weightage, it is less prominent in the output. Now, what if I change these values? Let's do one more experiment, right? Suppose if I give my image 1 lesser weight, my messy image if I give 0.3, my logo if I give 0.7. Now let's see the output. This output looks like this. So what has happened here? The logo has become more prominent here. Because I've given it a weight of 0.7, the messy's image has become less prominent. Ideally, you don't want to do this. If you want to put your logo on some image, you want your logo to be subtly present. Like for example, here I have a logo of Applied Roots, which is subtly present here. Right? It's not very dominant. It's there in some corner. Again, you can also place things in corners, etc. That's very, very simple. It's there in the official documentation, which I'll point you to in a minute. So this whole thing, I've given you this example, right? So if you just go to this, okay, so if you just go here, again, I've explained you one example of image blending. There are lots of other operations like bitwise AND, bitwise OR. You can also place OpenCV in a small region in the whole image. Like you can do all of that stuff. In the interest of time, I'm just taking one example. But once you know this syntax, once you know how to read the documentation, doing these simple operations is very, very straightforward and simple. Right? So this is our first problem. Before we go to the second problem, again, if you have any questions in the chat window, I'll take a few minutes to answer your questions, and then we'll go to the second question. Okay. Cool. So, okay. So, what is the math behind resizing? Nice. That's a good question. So, there are many ways of resizing. They are typically called as interpolation algorithms. The simplest way to resize, again, resizing images is a whole topic onto itself, but a simple way to think about it is, imagine if I have an image like this, some triangle here, right? Suppose if I want to change the size, suppose if I want to double everything, then whatever pixel I have here, I will replicate it as 2 pixels, everything that I have here. That's one of the simplest ways of enlarging something. But this is the simplest way, but the mathematics behind it is through interpolation. So let me just see if I can get a quick description of that. Image resizing. Again, it's a whole lecture length stuff. Image resizing math. 1 second. Okay, so here is something, but let me see if I can get the math behind it. Okay, these are interpolation methods, but in an essence, the simplest thing is you take, okay, so without going too deep into it, because I don't want to go into bicubic interpolations, etc. But the simplest thing is whatever value you have here, suppose this is h and w. I'll take the simplest example, right? Height h and width w. This is 2h and 2w, let's say. So you take each pixel, right? This pixel will be pasted as 2 pixels because the width is also getting doubled and the height is also getting doubled. So you place it in 4 pixel. If this pixel has some value v, right? The same values you place it in 4 places because you're doubling the height and doubling the width. This is the simplest form of sizing, especially if you're doubling the length and width. If you're not doubling, then you have to go into interpolation based methods, right? So there is a whole mathematics behind. Again, there are nearest neighbor, bicubic. Bicubic interpolation is something that is used extensively in image processing, but we'll not be able to go too deep into the mathematics of it. But you can easily find a nice description. Let me see if it is here. Wikipedia surely has bicubic interpolation. Okay, so yeah, here it is. Okay, there is no easy way to explain this without going into the math. But if you have time, this is a nice article to read. It also has some nice examples. I'm happy about this. So it has bicubic. I'm sure it will also describe other methods like bilinear, nearest neighbor interpolations, etc. So it's a whole area of image processing. Just rescaling images itself is a big topic onto itself. Okay, non-trivially big. But I hope you got a gist of what I was trying to tell you. So another question that somebody said is, what would gamma value do? Let's actually change the gamma value here, right? Let's see, where is the documentation here? The gamma value is simply added, right? Where is the documentation here? Resize. Oh, by the way, the resize function, right, has a lot of interpolation algorithms. Look at this. There is a whole list of interpolation flags. You can use nearest neighbor interpol. These are all the interpolation algorithms that you typically study in image processing type of course. Like I remember studying about bilinear interpolation and bicubic interpolation at undergraduate and graduate level image processing courses, because I've taken them both at undergraduate and graduate level when I was studying. Cool. What was I telling about? I lost. Okay, so what is gamma? So let's just change gamma and see what happens. Gamma should simply be added, right, to each pixel value. See, look at this. So the moment I change gamma to 100, look at this. Very interesting, right? So what did it do now? Look at this. So let me just explain this. Somebody said, hey, what does gamma value do? So initially we had a gamma of 0. Now I've changed it to 100. So what it is doing? It is doing 0.3 into image 1 plus 0.7 into image 2a. Whatever value you get, you are adding 100 to it. So the moment you're adding some of these values, what happens? Look at this. For each pixel value, as the value of the pixel becomes closer to 255, 255, 255, this is becoming closer to white and white and white. It's becoming closer to white, right? So what I'm doing here is for every pixel, after multiplying 0.3 into image 1, 0.7 into image 2a, I'm adding 100. The moment I add 100, what happens? The image becomes lighter. Because for each pixel, its values are coming closer to, because we're adding some value here, right? 255, 255, 255, it becomes closer to a white color. Now let me see if I can give gamma as a negative value. Let me just try it. Yes, see, look at this. If I give gamma as a negative value, for each pixel, the pixel values are going closer and closer to 0, which means it's becoming a darker image, right? So you can use gamma primarily to adjust the darkness or the lightness of the final image. That's one of the simplest ways of doing it, right? Look at this. That's a very nice question that somebody asked about gamma, right? Cool. Oh, let's see what happens if I add 255 as gamma. I think the whole image should become white, right? Yeah, the whole image has become white, right? We can try negative values also. So if I do minus 255, the whole image should become black. Yes, the whole image becomes black. That's a good question. See, these are very simple. The moment you know the math behind it, right? Again, that's why I've shown you the mathematical documentation behind add weighted. The moment you know the math, you know what is exactly happening, you can change these parameters very easily to get the results that you want. Because at the end of the day, what is this image? This image is basically 3 matrices. That's all. You're just adding and subtracting and multiplying matrices. That's all there is. Cool, cool. I don't know. I think I can give more alpha. I'll have to read the documentation. I don't remember the documentation by hand. But if you give a value that is too large, anyway, all these pixel values, suppose if I give a value of 500 here, anyway, the moment a pixel value becomes 255, it becomes full white. There is no point in adding extremely large values there anyway, right? Because whatever is the pixel value, if a pixel has a value of 255 or more, it will be treated as white. If a pixel has a value of 0 or less than 0, it will be treated as black, right? Simple logic. Again, this is very simple experimentation that we all can do. Cool. So let's go to the next problem, folks. This is slightly more involved, but let's go into it. Okay. Cool. Just give me a second. It's 8. So we should be able to solve at least 1 or 2 more problems. Okay. So let's take up this problem now. Again, the beauty of computer vision is it is so visual and satisfying because you see the results right away. I mean, when I was in graduate school at an Institute of Science, I literally fell in love with computer vision. Even though I was studying machine learning, I did so much of computer vision stuff on the fly because it's visually like cool. I mean, you see beautiful results in front of your eyes, and we humans love visual stuff. So computer vision is like attractive from that perspective, and you get to see results with 10 lines of code. Okay, cool. So now let's take up another problem. Okay, so here let's assume we want to detect new items or people in a surveillance video. Suppose imagine you have a surveillance video. I think I have a video here somewhere. Okay, so let me just play this video for you. Okay, let me just remove the audio. Okay, so here there is a surveillance camera here. Okay, what the surveillance camera is doing here is, okay, let me just show you here. Okay, so the surveillance camera is fixed, right? Typically your security cameras, right? So there are people moving and you want to track all the people or items that are moving. So if you observe here, there are people coming in, people going, even this small rope that is there is moving because of wind. If you observe this, look at this. The small rope is also moving. People are coming in, people are going, new people are coming in, people are going out, all of this stuff. So in a lot of video surveillance applications, you want to track everybody who is, again, in a video surveillance, what happens? This whole background is fixed. Look at this. Your whole background is more or less fixed because your camera is fixed. Of course, your background image might change when it becomes dark or when the sun rises and things like that. But if you look at from one video frame to another video frame, mostly these people are changing. The whole other rest of the background is not changing much. So can you detect that, okay, there is this person here in this frame? Can you do that analysis? Now, first and foremost, before we go in, again, it's a very important problem in video surveillance. Like lot of security cameras have this inbuilt, or they do it at the server end. Let's try to see how to do that. Now, I'll give you some mathematical foundation behind it first, and then we'll go solve it using OpenCV. Now, what is a video first? A video is literally a sequence of images. So this is your image 1, then you have your image 2, you have your image 3. A video is basically a sequence of images which are played fast. That's what an image is. That's what a video is. A video is basically a sequence of images. Typically, when you record with your smartphone, not in slow-mo, but in regular mode, you're mostly recording at 24 FPS or 30 FPS. So what does FPS mean? Frames per second. Each of this in video processing, each of them is called a frame. Each of these images is called a frame. So our human eye, the moment the video is played such that there are 24 frames or images that are played in 1 second, we think of it as natural video, right? So typically movies are shot at 24 frames per second. We also shoot at 30 frames per second. The slow-mo that some smartphones have shoot at 60 FPS or 120 FPS, right? The slow-mo shots, right? Like iPhone, even Samsung phones, a lot of them have this slow-mo mode where you're shooting more images per second. That's why you're getting a slow motion when you play it at regular speed. So at its core, a video is nothing but a sequence of images typically at 24 FPS or 30 FPS. Now, what is the simplest way to detect that a person has entered? Imagine that this is the scene. Okay, I'll just draw something very simple. Please, so let's assume there is a road here. Let's assume there is a tree here, right? Something like this, okay? Now, your surveillance camera is seeing this. Let's assume this is frame 1. Okay, let me write it down. This is frame 1. Now, you have another frame, right? After, like in the second frame that you have, let's assume the same tree will be there because these are just captured with just a few milliseconds between them, right? The same tree is here. Sorry, the same road is here. Road doesn't change. It is static. The tree, if there is strong wind, it might bend here and there. But imagine if there is a person who has come into this, right? Remember, what is an image? An image is literally 3 matrices if you're taking color images, right? So if you think about it, if you think about this as matrix A, and if you think about it as matrix B, okay, again, every time instead of saying that each image is 3 matrices, let's just think of it as one 3-dimensional array, right? You can think of it as a tensor, right? Okay. So now, if you do B minus A, what happens? Look at this. See, this is just a matrix, right? Or if you want to think about it, 3 matrices of RGB, 3 matrices of RGB. What happens if you do B minus A? What do you get? Because if you do B minus A, you will get a sense that something new has come in here. Because this pixel and this pixel, look at this, for all the static pieces, for all the parts where everything is static. So imagine the tree is not moving, okay? It's like a strong tree that is not moving. There is not much wind. So then this pixel and this pixel will exactly be the same. So when I subtract this pixel with the corresponding pixel, again, their height and width, this height and width are the same because it's the same camera which is shooting this video, right? So this pixel minus this pixel, it will become 0, right? So similarly, this pixel and this pixel, it will become 0 because they're the same values. But if you notice, take this pixel and this pixel, they're not the same. So if you take the pixel value on the human face and subtract it with this, you will get a non-zero value. So when you perform B minus A or A minus B, whatever you want to perform, you will get the image that you get now. The image that you get now will primarily have colors or non-zero values where the human is there or a new item is present in the video, right? So one of the simplest ways of finding new objects or items in a video or things that are moving, right, from one frame to other frame is to do image subtraction. This is the simplest way of doing it. But this has a lot of errors. There are a lot of problems, real world problems that you'll encounter. So there are advanced techniques that are built. Like this whole area is called image subtraction problem, right? It's again, just like image resizing, image subtraction has like literally thousands of research papers. Like there are tons and tons and tons of research papers on this, Okay, the simplest way of solving it is using image subtraction, like subtracting one matrix from the other matrix, or the three matrices from the three matrices. That's the simplest mathematics behind it. But the cutting edge methods, again, OpenCV doesn't just implement these image subtraction methods which are trivial, right? It implements more complex machine learning models. I will just discuss about one such thing briefly. Okay, so the state of the art in image subtraction uses machine learning and deep learning models, because if you really want high quality output. Okay, so first let's get the video, right? So if you go to OpenCV's GitHub, in the samples there is this vtest.avi, the video that I just showed you, right? So let me download it. What I've done here, again, webget, I'm just downloading this vtest.avi. Very simple, I've downloaded it. I've seen whether it is there. Yes, vtest.avi is there. Very nice. Okay, I've downloaded it 3 times to see if everything is all right. Yes, I've downloaded it. Now comes the fun part. Okay, just ignore this. Let me just remove this. This is not needed. I ran into a problem because of which I used FFmpeg. Just let me remove this. You don't need this. Okay. So now let's start writing code. We have downloaded the video. The video is called vtest.avi. Let's start writing code. We'll encounter some problems. We'll solve those problems as we go. Again, this code has been taken from this tutorial. There is a tutorial. Okay, so let me just copy this. So there is this whole area of problems called as background subtraction or image subtraction problems. Okay, so this whole area, so in OpenCV Python tutorials, which I just showed you a while ago, right? So there is introduction to OpenCV, GUI features, core features. There is one thing called video analysis. Within video analysis, there are lots of sub-problems like optical flow, etc. Background subtraction is one very popular problem. Okay, so we will solve this. So this problem is fundamentally called as image subtraction or background subtraction problem, because you want to subtract the background. There are tons of algorithms for it, right? Like we'll see how some of these algorithms work, but before we go, let's start processing the video that we have. Okay, cool. So again, this whole documentation is here for you to refer even at a later point. Very simple. I'm importing NumPy, I'm importing OpenCV2, I'm importing image show. So when you want to capture data from a video, right? So you use this function called as video capture. Okay, this is again in OpenCV. So I'm just writing cv2.video capture. So to video capture, you just have to give the video file, right? So the moment you do this, okay, I've just printed cap. When you print cap, it says, hey, what I have here is a video capture object, right? So it's just printing that, yes, I created a video capture object called as cap. Cap stands for capture. Now, if I run this line now, cap.read, okay, what it does is, in this whole video, remember a video is a sequence of frames. Right? It's literally a sequence of frames. The moment I say capture.read, it will take the first image and it will return this first image. If I call cap.read again, next time it will return the second image. If I again call cap.read, it will capture the third image. It will read or capture the fourth image, and so on and so forth. Right? So the first time when I say cap.read, it will capture the first frame and it will return. It returns two things, RET and frame. The frame contains the actual image. The RET, again, you can read this in the documentation for video capture. This RET will be equals to true if it could successfully obtain the first image. If it could successfully obtain the first image, it will return true. Otherwise, it will return false. Okay. Again, that whole thing is there in the video capture documentation. Let me just show you that. Again, it's very important skill for you to be able to. Okay, let me just open this. Okay, so OpenCV video capture class reference. Okay, let's see the video capture. Where is the Python documentation here? What does it return? File name, 1 second. Control F, return. Just a second. Okay, look at this. So video capture, I'm just looking for that. Oh, video capture.read, right? Sorry. Video capture read. Okay, so the function that I'm looking for is the read function. I'm sorry. Is open. Okay, read. Okay. So the read function. Okay, so CV video capture read. This is the function that we are using, right? This is the C++ documentation. This is the Python documentation. It returns a return val and an image. Look at this. So the image is what it has captured from the video. The return val is false if no frames are grabbed, right? You just have to read the documentation, that's it. Now what happened in my case was, again, whenever I write any code, I check whether things are working as expected. I printed return, it gave me false. Then I tried to print frame.shape, it threw an error. It said that it did not have, the frame is none type, which means nothing got captured from this AVI file. Okay, so then finally I released the capture, because capture is an object, right? The capture is an object, and capture is reading everything from this file, which is a video file. So I've just released all the resources. Now the biggest problem, I said, okay, everything looks right here. I don't have any major errors. Why is the return false? Right? So there is no syntactical error. This code is literally 2 lines of code. If you ignore the print cap, it's just a very simple problem, right? There don't seem to be any errors in my code. With some Google search, I realized that the Google Colab, the server that is provided, that is running Google Colab, does not have the tools needed, the libraries needed to access an AVI file. That is the problem here, right? So I just Google searched for it, and after some struggling, I realized that this is a problem with the AVI file, not with my code. So the Google Colab is not able to read AVI files because the Linux server on which it is running does not have the libraries to read AVI files. There is something called libavi which it needs, which is not there. Okay, so after some problem, I realized, okay, let's get out of this problem. So what I've done here is I've taken the AVI file, I've gone to my command line, my Linux box, or my Mac here in this case, right? So this is my Mac. All I've done here is, my Mac has all these tools. It has FFmpeg, everything. So all I've done here is I've downloaded the vtest.avi onto this is my personal laptop. Okay, this is my Mac, my personal laptop. All I've done here is I've used FFmpeg, and I've said FFmpeg is a very, very popular library that is used by you all know VLC player, right? VLC player uses FFmpeg extensively. It's one of the great open source libraries to convert videos from one format to other format. Okay, so you can just install FFmpeg very easily on your Linux box. Windows, I've never installed it, but Linux and Mac, it's very simple to install. So I just converted, so FFmpeg, my input is vtest.avi, my output is vtest.mp4. So I just converted into MP4 because I realized that, okay, AVI is not working on Google Colab, maybe MP4 will work. Okay, so I just did that. Then whatever file I have, I uploaded it to my Google Doc. Sorry, I uploaded it to my Google Drive. So first thing, I've converted it into MP4 on my laptop using FFmpeg, uploaded to my Google Drive, and I've made this available to all of you. Anything that you have on Google Drive, you can download it using this command. Okay, look at this. Exclamation, which means it will run on command line. Webget, just say no certificate checks. There is no need for any username, etc. It's publicly available. In my Google Doc, the Google Doc has this unique ID. So in Google Drive, in Google Drive, every file has a unique ID. So I just took that unique ID, pasted it here. That way I can download anything from my Google Drive. So I've just downloaded from my Google Drive. Now I have my MP4 also. Now I just reran the same code. The same code, instead of AVI, I ran it with MP4. Everything worked perfectly. Everything simply worked perfectly. So let me just run it again. Give me a sec. Okay, so AVI I don't need. Okay, there is a small bug, but let me run the code here. I think I reran it here. It should not take much time. Okay, good. So look at this. Okay, so I just reran it. When I ran it with, okay, let me show you this also. This had the error, right? With AVI, I had the error. So I moved to MP4, the same code, nothing changes. I created a video capture object. The video capture object is there. Then I read the first frame. It returned true, and it said the first frame has 576 rows, 768 columns, 3. Perfect. So it got me the first frame now. Okay. So if I want the second frame, I just have to call cap.read again. I just have to keep calling it. That's it. Now comes the most interesting part. Now, how do I do background subtraction? Now, one way to do background subtraction, which you can experiment with, is very simply subtract one frame from the previous frame. and keep looking at where changes are. That's one way. So but that's too rudimentary. If you really want good results, there is this method called as background subtractor MOG. Okay, so this is based on this research paper from 2001. So, okay, cool. So again, this is all there in the documentation. So I'm just using this OpenCV's implementation of this research paper. This is a slightly old research paper from 2001, but it's a fairly reasonably simple to follow research paper if you know machine learning. So this paper, like I just quickly went through it. It's just simply using something called as Gaussian mixture models to get a representation of the background so that it can subtract the background from foreground easily. So the reason I took this specific example here is your mixture of Gaussian distributions is very much like your k-means clustering. It's just a probabilistic variation of your k-means clustering. So the reason I picked this specific example is because to show you that lot of current techniques that are used in OpenCV are very much dependent on machine learning techniques. So your Gaussian mixture model or Gaussian distributions based clustering models or Gaussian mixture based background foreground segmentation algorithms, all of them are based on a technique called Gaussian mixture models, which is just a generalization of k-means, which is actually studied in machine learning typically, right? So what this research paper has done is it has taken a machine learning technique to perform better background subtraction. So if you really want to become good at computer vision, you first have to also know machine learning and deep learning. And there are also background subtraction algorithms today which are deep learning driven. Okay, so this is slightly old. This is almost 20 years old, but does a decent job, right? So let's see how to use this. Okay, I'll show you the documentation. I'll not be able to explain the underlying mathematics behind it because then I have to explain you about how k-means works. Then how do you do a Gaussian mixture model and all of that. That's beyond the scope of this discussion. But if you want to become a good computer vision engineer, you have to understand those internals, no doubt about it. And to understand those internals, you have to know machine learning and deep learning for sure. Because most of modern deep learning is just built on top of classical machine learning and mostly deep learning now. Okay, so let's get started. I'll explain the code on how to use this. It's actually very simple code, literally 10 lines of code. So what I'm doing here is this. Okay, so I'm importing, okay, let me use a slightly different color. Okay, I'm just importing my NumPy, my CV2, my video capture. Here, remember, I'm using MP4 so that there are no errors in the video capture, right? My video capture with AVI is not working because of some problem with Google Colab. So then this whole create background subtractor MOG, right? So the whole documentation for it is here, which I've just shown you, right? So this is the documentation that I'm talking to you about. So what I'm doing here is I'm creating an object now called foreground background, FGBG. Okay, I'm creating an object which is part of OpenCV2. There is a whole module called background segmentation algorithms. BGSEGM in OpenCV2 is basically a bunch of background subtraction algorithms. Again, this is a whole topic onto itself. Like we can spend 3-4 hours just going through. Okay, so look at this. OpenCV background subtraction algorithms. All these algorithms are implemented now, right? We are using one of them if I'm not wrong. Okay, there are tons of, we are using this background subtractor MOG. MOG stands for mixture of Gaussians. Okay, so we are using this probabilistic Gaussian model or probabilistic mixture models. So, but there are other algorithms, tons of algorithms. I'm taking the simplest of them here, right? So, okay, so the BGSEGM basically means background segmentation methods that are there. Within that, I'm using this create background subtractor using mixture of Gaussians. So this creates a background foreground subtraction object for me. Now I'm creating this variable called count to keep a count of how many frames I'm processing. So first I want to process the first 3 frames. Look at this, my count is 0. After I process each frame, I'll increment the count and this is a simple while loop, right? Simple while loop here. Again, I've modified the code that exists to make it work in Google Colab easily. Okay. So all I'm saying here is, let's see the first 3 frames. Okay. What are we doing step by step? First, we are reading or we are capturing from the video. We are reading one frame. On that frame, we are applying this foreground background algorithm, which is your background subtractor mixture of Gaussians algorithm. On that frame, we are applying it. right? When I apply it, what it returns to me is a mask. So this foreground mask basically means that it shows, the foreground mask can be thought of as a binary image. A binary image basically means it either has black or white. Okay, that's why these are called as masked images. So what it returns to me is basically a binary image where each pixel is either black or white. White corresponds to the foreground part, right? So foreground is basically where new items or new people are coming in. Background is a stationary part, right? So what are we doing here? We are applying this mixture of Gaussians method on the current frame, and it does some simple machine learning, basically a mixture of Gaussians approach, and it returns basically another image, which is FG mask. Now I can show this image, right? I will just show this image. I'll increment my count. I'll do it for the first 3 frames. Once I'm done, I will just release this video capture and I'm destroying all windows. So if you just execute it, let me just execute it for you. Takes a couple of seconds. Look at this in the first frame. Okay, so first frame, nothing is there because it's a first frame. Next frame, look at these 3 people. These 3 people. So if you notice this image, okay, let me just scroll down a little. This image is a black and white image because the code here, when you apply the foreground background mask on this, what it returns is a foreground masked image. As I just told you, it's a masked image with only black and white. So white pixels are those regions where it recognizes something different. So if you observe carefully, there is a person that entered into the scene here. There is a person here. There is a person here. And if you recall, there was this wire-like thing, right? So let me show you that in the video. So there was this whole rope, right? Rope or some whatever, some material here, like a boundary rope, which was also moving. Okay, let me just play this video for you. So in the very first frames, look at this. It is moving here, right? It is moving here. Even that got captured here. Even that got captured. Small area where things are moving. So this is the first frame. If you just go down in the second frame, again, this person actually moved ahead in the second frame a little, right? This person moved ahead in the second frame. So it's also capturing all of that information of the first person, second person for the first 3 frames. Very simple, right? So again, you don't have to just stick to the background subtraction using mixture of Gaussians. There are tons of algorithms. Again, each of these algorithms is like a, okay, where are these? Okay, so there are a bunch of these algorithms, right? So each of these algorithms is it's typically studied in a typical image processing course or a computer vision course. Of course, some of these which are slightly complex, like mixture of Gaussians, can be studied in a computer vision course because people expect you to know some machine learning there, right? So tons of algorithms. There is, I mean, the sky is the limit, to be honest. Again, I don't know many of these algorithms. I even read the emoji algorithm paper just yesterday when I was preparing for this live session, right? But you should have, as long as you have some basic foundational understanding of image processing, a little bit of matrix algebra, a little bit of machine learning, most of these should be understandable with some effort. Obviously, they're not trivial, but they're easy to understand. But you can use them. You can experiment with all of them, try around. Again, I think this background subtractor functionality also has something called as detect. Okay, let me show you this. Okay, so it also has, again, on the same video. Yeah, look at this. On the same video, this is the 200th frame. Look at this. In the 200th frame, it says that here there is a person, here there is a person, here there is a person. This whole rope is also moving and things like that. You can also have this option where you can show the shadows of people also, right? So there is this option where for this function, right, for background subtractor emoji, it can also detect shadows. Okay, shadows of people, light shadows of people, where there is a small change in the okay, look at this. It has an option called detect shadows equals to true. Okay, so if you keep this detect shadows equals to true, it can also detect these small changes in the lighting because of shadows. Okay, very simple algorithm, very simple to use, and there are multiple versions of these. There are multiple algorithms. There is mixture of Gaussians version 2 also. More interesting paper from, I think, 2006 or 2000. Yeah, so efficient adaptive density estimation, blah blah blah, from 2006. So for the same mixture of Gaussians, there are multiple implementations in OpenCV. So the sky is the limit. There are literally thousands of algorithms in OpenCV. I think even people, again, remember, all this is open contributions by hundreds of researchers over the last 15-20 years. So I don't think any single person knows all of this inside out. But if you know even some of them, that's a good start, right? So the key lesson here is most of the cutting edge computer vision techniques use a lot of machine learning and deep learning, right? So any questions related to this? One second. So any questions here? So I'll take a couple of questions and then I'll go into the third problem, which is actually simple convolution operation, which we can cover in a few minutes. So nice. Chetan has this question, which is where can you use bitwise operations, right? So here is a very nice blog. Again, you can use bitwise operations to combine images also. Where was this other example? The first example, right? Okay, so let's go to this documentation. Okay, let's go here. Open a new tab. So we talked about image, image blending, right? So just below that, there are these bitwise operations that you can do, right? Especially, so if you want to say, okay, so here is one result of the bitwise operation. So using bitwise operations carefully, again, the documentation is very clear, very readable. You can get a result like this. Look at the result here. This result is very interesting because you have Messi, you have the logo here, right? And in some pixels, the logo is there. In some pixels, Messi's hand is there. So the background and foreground are much better fused. And you can do this using some of the bitwise operations. Again, the reason bitwise operations are very, very popular in computer vision is because they're very cheap. They're extremely cheap. Right, so just look at this again. This code is very simple to read because you have some background now. You know what IMRead does, you know how to access various pixels. Very simple. Bitwise operations can be used basically to speed up computation a lot because bitwise operations are much more computationally efficient than arithmetic operations, right? So how to connect with a real time? Okay, so one second. Yes, so Umang has a very nice question, which is, does background subtractor create any difference in night light? So lot of surveillance cameras now have night mode. Lot of surveillance cameras that you can buy even on e-commerce websites, they have a night mode. And since most of the times you're only comparing one frame to the next frame, right? Even if it is night mode, from one frame to other frame, you're just having like 30 milliseconds gap, right? So if you have night mode enabled or night vision enabled, they can still work very well. But if you don't have night mode or if you don't have artificial lights, right, in the scene, you will miss it out. Again, at the end of the day, the camera also has to see, right? Without that, how can it detect things? Right? If there is artificial light like tube lights or street lights, perfect. Or if it has night mode, that's also a perfect way through which you can solve it. So how to draw a box? Okay, so that's a nice question. So I'll show you a simple way to do it. I'll point you to in the right direction. There is this whole, so if you go to OpenCV Python tutorials, there is this thing called GUI features. Okay, so just go to GUI features. There is this whole thing called drawing functions here. Okay, again, very simple to follow code. You can draw a line using CV. So you can take an image and draw a line. You can draw a circle. You can draw a rectangle. You can draw an ellipse. You can write text, right? Literally like, okay, so let me show you. Okay, is there any output? Okay, so there is this output, right? Very nice. Okay, it's actually literally 3 lines of code. Okay, let me just show you this. One second, I want to take an image and draw it on this. Okay, so here they have done it slightly differently. So, okay, let me just anyway walk you through this. It should not take much time, 2 minutes. So first look at this. First, what are they doing here? They're creating a black image. Look at this. They're creating a black image here. They're taking np.zeros, numpy zeros. They're creating a matrix of 512, or they're creating a numpy array of 512, 512, 3. And each value here is an 8-bit integer, unsigned integer, which means the values will be between 0 to 255. And they're initializing everything to zeros. So what do you have? You get, now what you get here is an image now because all RGB, all these three matrices, every pixel is a 0. So what you get is a black image. On this black image, right, on this black image, you can draw a line like this. You can say CV2.line. What do you want to draw it on? You want to draw it on this image. This is the starting coordinate of the line. This is the ending coordinate of the line. This is the color of the line. Red, green, blue. Oh, I think in, okay, so there's a small problem here. I think in OpenCV, it doesn't use RGB, it uses BGR. Okay, this is a small mess up with OpenCV. Let me see the final thing that we have here. Yeah, it's a blue line. Yes. So OpenCV, unfortunately, for some early reasons, it uses not RGB but BGR. Okay, so look at what it's doing. So it created a black image. In this black image, it is drawing a line from 0, 0. So it's drawing a blue. Okay, so it's drawing a line from 0, 0, which means from here to 511, 511, which means it's drawing a line like this. And the color of the line is blue line, and the thickness of the line is 5 pixels, right? So you have drawn, again, where is it drawn? It's drawn on the image, and the output is again IMG, right? Then it is drawing a rectangle on the same image. It's drawing a circle on the same image. Look at the final result that you get. You get this image with top left to bottom right blue line. It created a circle, it created a rectangle, it wrote some text, it created a semicircle. You can do all of this on any image of your choice, but it's actually very simple. It's literally like one line code for each of these tasks. Cool. Very nice. So there is this very nice question from Asim Kiran. It's already 8:33, right? So let me take some questions. I have one more problem which I wanted to explain. Okay, so I'll answer a couple of questions and then go to the third problem because I want to cover it so that you understand very important operation called convolution. Okay, I'll just start that. I'll answer one more question and go there. If required, I'll stretch the session a little longer. If you're interested, you can continue. Cool. What is the processing time of this library? This is by Asim Kiran. Very nice question. Most computer vision operations are computationally expensive because imagine how much compute it has to do. Even if the code is written in C, C++, it's still computationally expensive. So you can't run away from it. There are ways around this problem where instead of using the CPU, you can use the graphics processing unit or the GPU or the graphics card on your computer. So that way you can speed up some of these tasks, but that requires additional challenges, additional computation, additional resources. You require additional hardware literally, right? But these are non-trivial operations. These are computationally expensive. Okay, can we detect human behavior? Yes, you can do that. So we have done another live session, I think 3 or 4 weeks back on how to detect. Okay, so there was this live session that we did maybe a month or 2 back where we talked about how to actually detect, how to build a smart gym. Okay, so how to build a smart gym assistant. Okay, so this was one of the very interesting case studies that we've done live sessions on. So in this, we had to detect a person and we had to detect each of the joints and each of the, like you had to detect ankles and elbows, all of that stuff you had to detect. And while solving that problem, we discussed how to do this using OpenCV code. Of course, internally, even OpenCV code is using deep learning algorithms, right? So we have discussed this. It is possible to do it. Okay, so it's very, very doable, but it's just computationally obviously expensive. It uses actually a deep learning algorithm for detecting human joints. Literally, it can detect even your eyes, all of that stuff it can detect. It's using a TensorFlow model. Cool. Does OpenCV work well with Raspberry Pi? Yes. I have done a lot of interesting personal projects because remember your Raspberry Pi is simply a Linux box with limited compute on an ARM processor. Right, so I have a Raspberry Pi somewhere sitting here next to my desk. I'll have to look for it. But yes, you can run OpenCV simple operations on Raspberry Pi. You can't do a lot of heavy compute. It's actually used in a lot of IoT applications. Raspberry Pi along with OpenCV is used extensively. Cool. Let's tackle the third problem. Just in the interest of time, I'll come back to questions a little later. Okay, after we finish the third problem. Okay, the third problem is a more fundamental signal processing operation. Okay, so let me go here. So this is not as exciting as the previous example, but it is more foundational. Okay. The reason it is more foundational is because it uses a technique called as convolution. So the challenge here, the real problem here is how do you blur images? Okay. There are a lot of operations like image blurring which can be achieved using this very interesting operation called as convolution. Convolution is a concept from signal processing. It is not something that the machine learning guys or the deep learning guys or the computer vision guys invented. It's actually a concept from signal processing which is almost 70-80 years old, probably even longer. I'm sure it's the origins of convolution is much older than even 70 years. But it was first used extensively in signal processing and communications. But without going too deep into the mathematics of signal processing, convolution can be understood very easily using matrix operations. Okay, again, the same convolution that we're discussing here is the foundation behind convolutional neural networks, which are literally the type of neural networks that are used on all images and video. So all images and video today, or at least 99% of image-based and video-based deep learning algorithms are convolution neural network based. Again, in our course videos, when we learn about CNNs, we discuss in detail about what convolution operation is. We even have assignments where we ask students to implement convolution operation, right? So here I will talk about how we can blur an image using convolution, but the objective is not much about blurring, but to introduce the concept of convolution, which is much more fundamental, which is literally at the core of state-of-the-art convolution neural network deep learning architectures. Okay, so let's take up this. Okay, there is a very nice documentation again here. Just like the way I've just shown you a while ago, these documentations are really, really good. Okay, so you have this whole computer. So again, in OpenCV Python tutorials, there is this whole section called as, one second, where is this link here? Okay, so in this section, there is this whole thing called as image processing, right? So if you go to image processing, one of the things that you have is smoothing images. That's where I am right now. Okay, so smoothing images, so let me explain you the concept of convolution first, then we'll see how it can be easily applied to perform blurring. Okay, so convolution basically means a very, very simple thing. Okay, let me just explain it with a very simple diagram. Imagine I have an image here. Okay, an image is a matrix, right? So let's just take, there are three matrices here. There is a height and a width associated with it. It's just a matrix of numbers. Three matrices if you take RGB. Now to this I can apply a convolution. Convolution basically means I take a smaller matrix. Let's assume I take a 5 cross. Okay, let me draw this. So let me draw a matrix here of 5 cross 5. Okay, suppose imagine I have a smaller convolution matrix. Okay, I'll call it as C. Let's call this image as A. So when I'm doing A convolution C, this is not multiplication, it is convolution. Okay, so please don't misinterpret this star as multiplication. We are doing a convolution operation. So what convolution does here internally is, so this is a 5 cross 5, right? This is a 5 cross 5 pixels, and here there are some values. Let's assume this value is 1, 1, 1, some values. There are some values, let's just say 5 cross 5. So convolution, what it does is it takes this 5 cross 5 pixels, it overlays here. Remember, okay, so okay, let me just zoom in and show you that. Okay, okay, so okay, so let's take, I just want to do it very carefully. So we are doing a 5 cross 5 convolution, right? So let's take our original image. Okay, our original image has many rows, many columns, all of that, right? Many rows, many columns. Okay, it has many rows, many columns, etc. So when I say convolution with a 5 cross 5, this is also called as a convolution kernel. Sometimes K is used to represent a convolution kernel. So what it does is this. So we have a 5 cross 5, right? 1, 2, 3, 4, 5. So okay, 1, 2, 3, 4, 5. Okay. So your 5 cross 5 kernel, is placed on the top left corner first. Once you place on the top left corner, let's just assume simply that all of these values are 1, 1, 1, or let's just say they're 1 by 25. Let's just say each of these values here are 1 by 25. I'll tell you why I'm taking 1 by 25, because we'll use it for blurring a while later. So there are 25 values here in this matrix. Each value is 1 by 25. If I sum up all of them, I get 1. Okay. So what happens here is, let's assume in the red value, right? So let's assume this is some 100. This is 101. This is some 100. So again, this is one of the matrices. Let's assume this is the red matrix for the image, right? So let's assume there is 126. There is 101. Some values like this. So what convolution does is, look at this. This white pixel had this value of 1 by 25. So we take this 100, we multiply 100 with 1 by 25. Then we take this 101, which is the value of this of the larger matrix. Then we do 101 multiplied by 1 by 25. We are multiplying with 1 by 25 because each of these matrix values are 1 by 25. Plus, okay, we take 100 multiplied by 1 by 25. So what we are literally doing here is, we are taking the values of the larger matrix, of our matrix A. We are taking each of the pixel values. We are taking each of the pixel values in our larger matrix. We are multiplying with the corresponding pixel value in the kernel, and we are summing up all of these. So there will be literally 25 multiplications and 25 all these values will get added, right? What would it generate? See, there are 25 such multiplications, there are 24 such additions. After you do all of them, what do you get? You get one number. That number is the value of the result. So let's assume A convolution K, let's assume, is another matrix B, right? For this matrix B, in the 0, 0 cell, whatever is the value of this whole summation, okay, of all these 25 values multiplied and then added, that will be in the 0, 0th pixel. Once this is computed, again, next, this kernel will move to the right, so we start the kernel in the top left. Look at this. We start the kernel in the top left, placing. Then we move it one step to the right. So literally what we're doing, convolution basically is, you take this matrix or the kernel, convolutional kernel, you keep placing it on each of the possible places that you can place here. So first you started off, you placed it in the left corner, then you moved it by 1 pixel, right? Then you again move it by 1 pixel. Every time you move it by 1 pixel, you will get one more result here. After you move the whole rows, then you go down, 1 pixel down, 1 pixel down. So this is literally like multiplying the elements of this kernel matrix with the elements of this matrix and then summing it up to generate this output. This is the core of what convolution is. Again, in the interest of time, I'm not able to go too deep into it. In our course videos, when we explain convolution neural network, I spend a lot of time literally writing code, explaining it in much more detail. But this is the core idea. It's computationally very, very expensive. Look at this. You have to place this on each. You have to keep moving it h times here, w times here. You're going to literally do millions of multiplications and additions to arrive at your result B, right? This is what is called convolution. Okay, convolution basically is an operation where you take a larger matrix like A and you take a smaller kernel and you place this all the values that you have in this kernel, you place it at each of these locations. You start with the left top corner, you keep moving right and bottom till the time you reach this corner. And when you place it on each of the possible locations, it generates one value which are filled in this. So when you do this convolution, you get B here. Okay, it's fairly computationally expensive, but it can be done on modern CPUs reasonably well. Not bad, because it's just basically multiplications and additions, right? Nothing very complex than that. It can be done fairly well. Now we can use image convolution for blurring the images, right? Look at this. So the intuition behind it is very simple. If you have 1 pixel, let's take 1 pixel here. Okay, this has some value, right? So now if I take all the pixels around it, a bunch of pixels, let's say 5 pixels rows, 5 rows and 5 columns around it. If I take all these values and if I average them out, look at this. If I have 1 pixel here, let's take 1 pixel here, this red pixel. Now if I take all the values around it and if I average that value out and give it as the final resultant for this pixel, right? The final resultant here is the average of all the pixels around it. let's say 5 pixels at 5 pixels in length, 5 pixels in height. Then what happens? This pixel will look as if it is the average. So you are literally doing, if you take the average of all of these and place it as the value here, it will look like blurred because you're taking information from all of these regions and placing it here. So this is how you can do very simple image blurring. And how do you do averaging? Averaging, you can do it by creating a kernel like this, where the kernel matrix is 1 by 25 so this is a 5 rows and 5 columns kernel, and each of the values here is 1 by 25 because there is 25 here, right? So whenever you pass this kernel or whenever you perform this kernel convolution on any pixel, look at this, when you perform this operation on any pixel, you're going to take all the values of all the pixels around it and you're simply averaging it. So convolution is one way of averaging if you're using this sort of convolution kernel. So when you actually execute code with this, right, let me just show you some simple, literally 5 lines code for it. Okay, so very simple. We are reading the OpenCV logo. We are showing this image. This is the normal image. Now on this image, if I start applying a kernel, so let me define this kernel here. Okay, so what are we saying? This kernel is numpy ones. Okay, each value is 1 of size 5 cross 5. Each value is a floating point value. Now all of that I'm dividing it by 25. So what do I get? My kernel is basically a 5 cross 5 where each value is 1 by 25. Each value is 1 by 25. That's what is my kernel, right? Once I have my kernel, I can apply my kernel on the image. I can simply say CV, OpenCV, filter 2D convolution. So the convolution that we just talked about is called 2D convolution because the convolution matrix is a 2D matrix. There is also something called as 1D convolution that we discuss in deep learning, right? But what we're doing here is 2D convolution, right? So what we're doing here is we are applying a 2D convolution filter on the image using this kernel. Very simple. Now this -1, I'll have to look at the documentation. I don't remember it by heart. So let me see this. What is this -1 here? Documentation. OpenCV, smoothing images, all these are tutorials. Okay, let's see. CV filter 2D. Haha, okay, so filter 2D is, okay, what are all the variables that are here? Source, okay, where is the Python documentation? D depth, what is D depth here? It is desired depth of the destination image. So this D depth is basically saying, if you have, see, look at this, the depth of the image is nothing but the number of, so the depth of our color images is 3 because it has literally 3 matrices corresponding to R, G and B, right? So by leaving the D depth to -1, we are not touching anything in the depth. Okay, the destination depth, we are not touching it. We are, whatever is the input depth, which is RGB, we are keeping the same thing for the destination also. Okay, so all that we are doing here is on this image, we are applying this kernel. It takes a while to run this, but if you see the output, look at this image. This is not sharp. This is slightly blurred compared to this. Look at this edge. It's very, very sharp here. This, look at the edges here. They're very sharp. Look at this. This is slightly blurred. This is slightly blurred, right? And this is a 5 cross 5 kernel. Now, if I increase the size of the kernel, look at this, instead of a 5 cross 5 kernel, I'm using a 10 cross 10 kernel here. Look at this, if I'm averaging more pixels, for each pixel, for each of these pixels, instead of taking a smaller kernel, if I take a bigger kernel, which means I'm averaging more and more pixels, which means it will get blurred more and more intuitively, right? So instead of 5 cross 5, if I take 10 cross 10, of course, I should also divide it by 100, right? Because I want because for blurring, one of the simplest things is to have all pixels the same value of 1 by 100 here. Now, when I do this, look at this. This is far more blurred. This is like your doctor's test, right? When you go to an ophthalmologist, the eye specialist, right? So this is far more blurred than this. Here we have used a 5 cross 5 convolution. Here we used a 10 cross 10 convolution, and the raw image is very sharp, the original image. So convolution is a very, very important operation. Again, the objective of covering this image blurring is to introduce you to the concept of convolution, which is literally like, in today's world, it is probably the most important operation because it is at the heart of whole of convolution neural networks. One more very important thing I wanted to teach you or just point you to is, just please go to this documentation. There are a lot of parts here. Literally, like if you go to Introduction to OpenCV, it talks about how to install on Windows, how to install on Ubuntu, all of that stuff. If you're using Google Colab, you don't have to worry about that. It's already pre-installed. The GUI features, right? I talked about how to draw shapes. So this is a very nice overview, and these tutorials are very, very well written. With this basic introduction, you should be able to follow most of them. Of course, there are some slightly complex topics like camera calibration and 3D reconstruction, right? This is your multi-view geometry. If you don't know the mathematics behind it, this can be slightly confusing, right? Because it talks about camera calibration, stereo images. You have to know some of the math behind it. So again, there is a whole new there is a whole new section called object detection module that is created recently to detect faces, people, body joints, all of that stuff, right? So very nice tutorial here. Cool. Let me just change the screen. Cool. So let me answer some of your questions now. Again, I'll share this whole thing. Let me just share it with you anyway, since we are here. I'll just share it with you and answer your questions in a second. Share. Just give me a second. Copy link. I'll just paste it in the live session here. Okay, I think I just pasted it somewhere, and yeah, I just pasted it from our thing. Okay, cool. Okay, so let me try to answer a few questions. Again, since this is a public session, it might be impossible for me to answer all the questions, but I'll try my best. Okay. So, okay. So Trojan has a very nice question, which is how to determine the kernel value and how it impacts image processing. Again, that's a very nice question, and that is a big area of what image processing covers. In a typical classical image processing course, you learn about lots of kernels. There is something called as Gaussian kernels, right, which are often very, very popular with image blurring. So there are literally hundreds of kernels that are designed by experts for different tasks. There are something called as denoising kernels, which are helpful to remove the noise in an image. Similarly, there are kernels that are designed to detect edges, like vertical edges, horizontal edges, and slanting edges. So if you take a typical computer vision or an image processing course, you will come across hundreds of these, which are handcrafted. So the difference between classical image processing and deep neural networks is in convolution neural networks or deep learning, these convolution kernels are learned from the data to solve our problems. In classical image processing, they're all handcrafted. I mean, they're literally research papers on thousands of kernels. Why is it 1 by 100? Because we want to average, right? So if you have a 10 cross 10 grid, look at this. If you have 10 cross 10 kernel, you want the sum of all these cells to be equal to 1, right? Just like the way we use 1 by 25 for a 5 cross 5 grid, right? So once you have 10 by 10, each of the values in this kernel matrix will be 1 by 100, right? Because we want to average. Averaging basically means sum up everything and divided by the number of elements, right? That's why we are using 1 by 100 there. How to blur a specific part of the image? That's a nice question. So what you can do there is very simple. You take the larger image, you can get a sub image, right? We saw the football example in the Messi's case, right? We only took a part of the image. So take the bigger image, get the sub image, blur that sub image, and replace in the original image those pixel values with the blurred image. Very simple, right? Again, remember, this is just a matrix. What you should remember here is your image is a matrix. You can remove, you can change, you can cut, you can do all of that on your images or your matrices. Praveen is asking about canny edge detectors. Again, edge detectors is a whole topic. I don't think we have time now, but they're very simple to understand. Once you understand the concept of convolution, your edge detectors are basically they're like some 20-30 very popular edge detectors like canny, etc. Now, if you have this edge detector, you can simply again, edge detection. The canny edge detector has a special purpose kernel which will detect edges in specific orientations like vertical or horizontal or slanting, right? So edge detectors is All your edge detection, most of the classical image processing edge detection is just applying a specialized kernel, right? And doing a convolution on top of it, just the way we have done it for blurring. So can you share a roadmap to learn OpenCV? Again, the roadmap that I would recommend is the documentation that I've showed, right? The tutorial from OpenCV, right? That's the roadmap. Let me just show you here. The roadmap that I would suggest here is, this link is provided in the, so start with the first one. Start with introduction to OpenCV. See if you want to install it on your laptop. Otherwise, just use Google Colab. Start with GUI features. My recommendation to you is go through each of these examples. You can just do it in Python. Okay. Try to execute each of these lines. Try to go through this in the given order. And when you're solving it, try to read the documentation. For example, you have image read. Go through the documentation for it. See what it does. Okay. Just read the documentation at a high level. I think if you can just go through even half the examples of these tutorials, which are there in OpenCV Python tutorials, even half of them, you'll become pretty good at OpenCV. So the OpenCV, thankfully, since it's a very old and also very mature library, there are tons of these brilliant tutorials here. Just go in the same order. Maybe you want to skip something like camera calibration and 3D reconstruction if you don't know the mathematics behind it. Again, the mathematics behind it is slightly intense. If you don't know it, you can skip it. Rest everything you can just follow. Just follow these tutorials one by one. That's all you have to do. That's a good roadmap if you want to pick up computer vision or OpenCV specifically. So averaging is the simplest form of blurring. So for blurring, very often what is used is called a Gaussian blur, right? Where your kernel, so if you know what is a Gaussian distribution, right? A simple Gaussian distribution has a peak value. In the center, it has a peak. As you keep going away from the center, the values are much, much smaller, right? So it's like this. So your kernel also, the kernel values are also placed similarly. The center of the kernel has a large weight, right? And as you keep going to the corners of the kernel, the weights become very, very small. That's what is called a Gaussian kernel, right? It is very similar to your, again, please don't get confused with the Gaussian kernel in computer vision with kernels in support vector machines. Those of you who know machine learning, don't get confused. They're two different ideas. The same kernel is used in the kernel used in computer vision is for convolution. The kernel used in support vector machines is for projecting data into higher dimensions, right? So they're different things. Is it possible to make a sharp image for blur image? Again, there are convolution operations. You can just Google search for it, wherein you can get sharper images. Again, what is a sharp image? You take a blurred image, you get all the edges. Suppose there is a triangle, right, in an image. You get all the edges and you highlight those edges. That's all. So you can also sharpen images. You can denoise images. You can find vertical edges, horizontal edges, slanting edges. All of that using just convolution operation. It's again in some of the tutorials that I've shared, it's there. Yes, so Umang has a nice question, which is, do a lot of these image and video processing, video editing tools use OpenCV? Some of them use OpenCV, some of them have built their own replica of OpenCV. For example, if you take Adobe Photoshop, right? I don't think they use OpenCV explicitly because OpenCV has some license issues that they might run into. But I'm sure they've implemented most of the functionality that is there in OpenCV in Adobe Photoshop. So you can actually build a micro or a small version of Adobe Photoshop using OpenCV. You can do that, or even video processing libraries. Is it possible to measure the speed of a moving object? That's a good question, Agnihotri. For that, you need to have some context, right? For example, let's assume you know that a typical person is, let's say, 6 feet tall. Let's just assume, or 5 feet tall, some number. So in image processing or computer vision or video analysis, if you want to measure anything, you need to have some reference measurement, right? For example, if you know that a typical car has these dimensions, then you can measure its speed, or you can estimate its speed reasonably well by seeing how the bounding box around the car is shrinking or is expanding, right? Look at this. You can use standard object detection techniques to detect a car. Now, if you want to estimate how fast the car is moving, all you need is you have to see how fast that box is growing or shrinking, right? If it is coming towards you, the box size will increase. If it is going far away from you, the box size will reduce. Now to do that, you need to have some reference measurement. Again, that's why most of these measurements are not perfect, but they're reasonably accurate. So there are some of these smart driving assistant systems which predict what is the speed of the car ahead of you. Now they do that by using the speed of your current car using the GPS, roughly getting an estimate, and then estimating relative to you how fast the car ahead of you is moving by computing the size of the bounding box, the rate of change of the bounding box size increase or decrease. Simple calculus that you can put in. Again, some heuristics also, but you can do that. Can you improve the clarity of images using OpenCV? Yes. So let me just show you an example. So in the same example, there is this thing called median blurring. Again, by the way, very interesting idea. So imagine if you're given a very noisy image like this. You can clean up the image by just taking the median in each grid, right? Because median is very resistant to noise, as we learn in statistics, right? So you can do some of these very simple image denoising also using things like median blur. Okay. There is also this bilateral filtering, but I thought, okay, let me just show you this. Image sharpening OpenCV. Again, any task that you want to do, okay, unlike blurring, okay, so here is a very nice, I hope it's a nice blog. Filters, arithmetic operations, okay, add and subtract, okay, to demonstrate this. Filters, blurring and sharpening, okay, so typical blur, okay. He's just explaining the concept of convolution in a detailed write-up, very nice write-up. Now, is there something where he shows image sharpening? This is blurring using a 3x3 kernel, using a 7x7 kernel. Okay, but what about sharpening? So look at this. This is the original image. This is a sharpened image. So to do the sharpening, he's using this kernel. So look at the kernel that he's doing here, right? So again, very simple code. I just Google searched image sharpening using OpenCV. He's using this kernel, this 3x3 kernel he's using, and on top of the original image, he's just applying this kernel. Rest of the code is very similar to what we have just seen. Now, if this is the original image, this is the slightly sharpened image, right? So you can do some of the sharpening even using simple convolution. Again, for every task or for some of these tasks, if not all of the tasks, there are specialized kernels designed like this, right? So let me also show convolution kernels. I'm sure. So this is again the mathematics here is slightly heavy duty, but look at a good chunk of kernels here, right? This is identity kernel, which means it doesn't change the image. Then these are edge detector kernels. Look at this. It is detecting some of the edges here. This is a sharpening kernel. Okay, this is a box blur, Gaussian blur. Okay, so these are some of the popular, so unsharp masking based on Gaussian blur. Okay, so these are some of the, like, this is a sharpening sort of kernel here. With this, you can sharpen the image. So this is the original image. You can sharpen it slightly by doing this sharpening kernel, right? So these are some of the, again, there is also very nice code, very nice. Actually, I like the pseudocode here because this pseudocode actually shows you how the kernel is applied. For each row, for each column, you apply the kernel, you multiply each of this. Very nice code, very nice pseudocode on how the convolution kernel is actually applied. Very simple code. Again, it's a very nice source that I forgot to mention, but let me just put it here. Let me put it in this. Okay, let me just put it here because that resource is very good. Okay, very nice. So I just added it to a document. So please refer that. I forgot about this kernel. So very nice write up here. So you can do some of these operations for sure. Cool. Where are we? Okay, cool. How to compare images and in a folder delete duplicate images that are labeled. So okay, so this is a very interesting task by Saurabh, right? So Saurabh says, imagine if I have a folder with a lot of images and I want to direct duplicate images and get rid of them. So for this, there is this concept in computer vision called as image statistics. So wherein you take an image and you represent that image as a simple vector. This vector can be computed using deep learning methods, or it can be computed using simple image processing stuff. For example, this vector could be a very simple way of thinking about this vector is this vector can say, hey, what is the distribution of red colored pixels? What is the distribution of green colored pixels? What is the distribution? The probability distribution. That's what I mean when I say distribution. What is the PDF of red color pixel values? PDF of blue color pixel values, PDF of green color pixel values, right? Now, if the images are exactly the same, these distributions will 100% match, which means that's most likely a duplicate image. Again, this is one of the simplest image processing ways of solving it. There are more complex ways of doing it where you find unique features in the image. Again, in OpenCV, there are these features called as SIFT features from computer vision. You can find unique features in an image and you see how many of these features match between two images. If a lot of these features from one image matches to the other image, that shows that the two images are duplicates. There are many ways of solving it, from simple probability distributions to cutting edge deep learning based methods. But those are the directions that you can pursue. So Manoj has a question, which is the updated document will be shared with you. Don't worry, because I updated the same document whose link I've just already shared, right? So don't worry about it. I'm just updating the same document. Okay. So for those of you who may have missed it, again, I'll post it in the description section of this video. So don't worry. So Manoj has a question, which is, does TV and film industry use image processing? A lot. Like we also do some simple audio processing, simple video processing and things like that, right? So they use it extensively. Forget about small studios like ours. Like they use all these advanced, like there is something called as FCPX on Mac. There is Adobe suite of tools, right? Like again, Photoshop, all of this stuff. These guys just use that. They don't, the TV and film industry guys don't implement these algorithms. They use tools built by companies like Adobe, which build these tools for them. So, this is Mactavish. He says, does a gap of 3 years affect my MTech CSC placements? No, don't worry about it. As long as you've gotten, again, I understand that you are preparing for ESC earlier. And if you got a good rank in GATE CSC now, just join. And most likely nobody cares. If you perform well in your MTech, if you have good CGPA, of course the interviewer might ask you and you can say, hey, I was preparing for ESC and other civil services during that time, and later on I just gave up on it and I got into MTech CSC, and here I am. Most people will not bother too much about it. If you have done well in your MTech, if you have good CGPA in your MTech, that should be all right, not a problem. So Chetan has a question, which is, can we draw bounding boxes of Apple images? Yes, Chetan. So in OpenCV documentation that I just showed, there is this module called object detection, right? Which uses models which are already trained with thousands of classes. So in deep learning, there is this data set called as ImageNet dataset with thousands of class labels, including your apples. So if you have, the model is already trained on like millions of images. So if you just give it an image, it will detect that here is an apple, here is a cat, here is a human. It detects all of that. Standard classes that you encounter, it already detects that fairly well. And you can do it in OpenCV or you can do it in TensorFlow. There are multiple ways of solving the same thing. So again, Akshay says, how do you do character detection? Again, there are at least 20-30 algorithms for it. The simplest image processing old school algorithms for character detection are basically detecting if there are too many edges. Look at this. If I write A here, there are too many edges there. So it just counts and measures if there are too many edges in any region, most likely there is a character there. Those are the old classical computer vision image processing techniques. More cutting edge techniques detect images by just training a convolution neural network on a lot of images which contain regions where there is some text, and CNNs, they learn the kernels that are needed, right? So for a lot of these object detection tasks, CNNs are not just the state of the art, they are the default option nowadays, right? Cool. In a small muted video of a person speaking, can we find out what the person is speaking? I think that's a hard challenge. It's a non-trivial challenge. Even for humans, it's a very hard challenge. Again, I've never encountered, or at least I've not read research work which solves that problem. So I don't think I have enough knowledge to comment on it. Yes, YOLO is available in OpenCV. Yes. So the beauty of OpenCV here is you can take any deep learning model and you can use it as part of OpenCV. So YOLO, you can use it in OpenCV. We've done it in one of our live sessions also. You can use it, you can use YOLO using the code base that the YOLO developers have given. Both of them are okay. I would personally prefer using the original developers code because it's optimized. It runs very, very well, right? YOLO, like we've done multiple sessions on YOLO v2, v3, code walkthroughs, etc. for in multiple live sessions earlier. So that's already there. Okay, folks, I'll sign off. It's already 9:12. Thank you very much for taking the time to join this session. And I hope this gives you the starting point to explore more of OpenCV and enjoy it. It's ever since my graduate school days, even my undergraduate days, ever since my BTech third year, final year, ever since I learned image processing in my BTech third year, I've fallen in love with OpenCV. Phenomenal tool. I've used it over 15 years now. And I hope you also fall in love with it and build some very interesting stuff, right? So all the very best. Bye-bye.